Hello and welcome to my video. I'm a math tutor, and linear equations is a topic I really enjoy teaching my students. The problem is, it is an area where the math gets a lot more abstract, and students lose sense of what really is going on behind the math or why it's meaningful, my high school self included. But as an educator now, I realize that linear equations are in fact really simple at its core. So in this video, I hope to illuminate some of the mysteries students have surrounding this prominent area of math. Let's first consider a concrete situation, one that literally came up with one of my students. A few months ago, I met a student who was really good at cutting hair, and he was cutting other students' hair for $15 per haircut. He enjoyed telling me about it, so we used that to talk about math. How much money does he make after one haircut? $15. How about two haircuts? That's 15 times $2, which is $30. And we can also phrase the previous line in terms of a multiplication as well, just 15 times 1. After 3 haircuts, he makes $45. And after 4 haircuts, he makes $60, and you get the idea. To compute his profit, we're just multiplying the number of haircuts that he performs by the amount that he charges for each haircut. In terms of math, we have this equation. Profit is equal to 15 times the number of haircuts. Now, we'll be doing much more math with this equation, so I don't want to write out these entire phrases each time. Therefore, we'll be using variables, like so. Variables are simply letters that we use to represent quantities that can take on multiple values, in this case profit and number of haircuts. We're calling this profit the letter P, and the number of haircuts the letter N. In the calculations that we did above, we chose N to be 1, 2, and 3, and we computed their corresponding P values. Having formed an equation containing variables, we reach our first vocabulary word. An equation containing two variables describes the relationship between two changing quantities. For instance, our equation right here describes the relationship between number of haircuts and profit. Let's take a look at a couple more scenarios to better grasp how we can use variable equations to talk about the world. Suppose that we're driving along a freeway, and we leave our home driving at 40 miles per hour. This equation below describes the relationship between the hours we spend driving and the total number of hours between us and home. Distance from home is equal to our speed of 40 miles per hour multiplied by the number of hours driven. And here it is in terms of variables. Let's let d represent the distance from home and let t represent the time, that is the number of hours we spend driving. It's still a pretty familiar concept at the core, it's just now we're speaking about it in the language of math, as an equation containing variables. And side note, I choose not to write the time symbol between 40 and t, but just know that putting them together like that means multiplication. Like the haircut example, we can choose different values for t, top right, and generate their respective distances from home. When t equals 0, which is the beginning of the trip, then our distance d from home is 0 miles. When t equals 1, which is 1 hour into the trip, then our distance d from home is 40 miles. When t equals 2, then d equals 80 miles. And when t equals 2.5, then d equals 100 miles. And just note, I chose 2.5 instead of 3 to demonstrate that we can also plug in fractional quantities for t as well. Now, what if instead of starting our drive at home, we started 10 miles away from home? How would our equation change then? For reference, I rewrote our previous equation for distance. Let's take a look at the diagram. However long we choose to drive, this is the distance that we cover in that chosen time. This distance is 40t, since we haven't changed the speed at which we drive. And since the entire distance from home d is the sum of the 10 miles head start that we had with the distance that we drove, our total distance from home can be modeled with this equation. D is equal to 40t plus the head start that we had, which was 10. And expectedly, this is very similar to the last problem. We just have an extra 10 tacked onto the distance because we had a 10-mile head start. We can plug in values for time, like before, to compute the respective distances from home. When t equals 0, which again is the beginning of the trip, the distance d from home is 10. When t equals 1 hour, we drove 40 miles, so d is equal to 10 plus 40 miles, equaling 50 miles. And for t equals 2 and t equals 2.5, we just repeat the same calculations. In the spirit of playing around with things, let's change the scenario again. What if the car started 120 miles away from home, and rather than going away from home like before, it headed towards home at the same speed of 40 miles per hour? How would we write an equation for d now? Okay, so there's several things here, so let's take it one step at a time. I'm headed towards home, so as time increases, the distance between me and my home should decrease. So rather than have a positive 40 times t, I want to have a negative 40 times t. In general, we use negative coefficients like negative 40 to represent decreasing trends. Next, it can be a little awkward trying to visualize where the 120 miles should come into our equation. There are several ways of doing this, and the way I'll show you is through a little algebra. When we plug in 0 for t, the value for d should be 120. But we have a problem. When we plug in 0, we get that d is equal to 0, which is not the 120 the situation requires. There is fortunately a quick fix. I can just add a positive 120. Now when I plug in 0 for t, d is equal to 120. In the end, we logically came up with this equation: negative 40t plus 120. And let's see if this equation actually makes sense for different values of t. Let's plug in values for t like before and check the results we get against our own logic. When t equals 0, our equation claims d to be 120. This makes sense because I start 120 miles away from home when t equals 0. When t equals 1, then our equation claims d equals 80. This still makes sense because after 1 hour, we will have driven 40 miles towards home, reducing the distance to 80 miles. When t equals 2, our equation claims d equals 40, which also makes sense by the same reasoning t equals 1 made sense. And when t equals 3, our equation claims d equals 0. This also makes sense, because in 3 hours we will have covered 120 miles, returning us back home. So we get that in the end, our equation checks out. Now, let's discuss something a little different. In all the driving scenarios so far, we collected these data points, these time-distance pairs. When you see data in the news, you don't really see it written out in this extended word form, but rather, you see data represented in a graph. For example, here, they had some equation that relates time to COVID hospitalizations, and they modeled it as a graph as opposed to writing out the data like we did. When we graph out relationships, it can actually reveal a lot of insights. Here, for instance, I can easily notice peaks and troughs in the number of COVID hospitalizations over the course of the pandemic. These trends would be harder to observe if I didn't graph it. Now, let's actually graph our distance problem to see what insights we can find. Here's our data from our original d equals 40t equation, written out in a table format. Just take a few seconds to refamiliarize yourself with the data. At the right, we have an empty graph, where the horizontal axis along the bottom is time t in hours, and the vertical axis along the left is distance from home d in miles. Let's begin graphing. The point 0, 0 is at the bottom left. For the next point 140, we go 1 unit along the t-axis, and 40 miles up along the d-axis to give us that point. To graph 280, we go 2 hours along the t-axis and 80 miles up along the d-axis, which gives us that point. And we can repeat the same process for the next 2 points, 3,120 and 4,160. There also exist other points in between the points that we just graphed. What if t equals 0.5, which is half an hour? Then by that time, we will have only driven half of 40 miles, which is 20. So we have the point 0.5, 20, which in graphed takes its place over there. And we can also drive, say, t is 2.75 hours, which when calculated will land us at 110 miles. And its point is there as well. You may be noticing something. As I'm graphing more and more points, all these dots are forming a straight line. And you would be right. If we keep graphing points until infinity, we would eventually get the image of a straight line. And that is why we call equations like d equals 40t linear equations, because when you graph them, they form a very neat straight line. Before we move on, I want to introduce some more vocabulary and some symbols you're likely familiar with already. All linear equations have a dependent variable and an independent variable. The independent variable is a quantity that we choose or control the value of, like how many hours we drive, or how many haircuts we do. And the dependent variable is a variable that responds to what the value of the independent variable is, like how distance from home responds to t, or how profit responds to n. In general, when we're not working with any particular scenarios, we use the unassuming variables x and y to represent the independent variable and dependent variable. Now, if all these concrete examples make sense, I suggest that whenever you work with x and y in your math classes, you think of them as hours and distance, or numbers of haircuts and profit, to hopefully make the math feel more concrete and natural. From now on, we'll sometimes be using x and y, just so we can get more comfortable with using abstract variables. Now, going back to the distances scenario, what if we increased our speed from 40 miles per hour to 50 miles per hour? To the left is our new equation, d equals 50 times t, and some of its data points. And here is the data graphed and connected in the same manner as the 40 mile per hour equation. Now, aside from the color change of the line, do you notice anything? The main difference is that the new line for going 50 miles per hour is steeper than the line going 40 miles per hour. That's kind of neat, and it also makes sense. Since going 50 miles per hour is faster than 40 miles per hour, if t increases by 1, then we expect the 50 miles per hour car to cover more miles, which means faster vertical increase along the d-axis. What if we decreased our speed to 30 miles per hour? Here's the equation and data points for that, and here's the graph for that. Notice that this line is shallower than the 40 mile per hour one. And again, this makes sense. Since 30 miles per hour is slower than 40 miles per hour, if t increases by 1, then we expect the 30 mile per hour car to cover less miles, which means slower vertical increase along the d-axis. We're making some great observations here. If I increase my speed, the line goes steeper. If I decrease my speed, the line goes shallower. And it turns out the other way around is true as well, which is, if I was just given these graphs without all the information to the left here, then having a steep line tells me that the driver was going at a fast speed, and having a shallow line tells me that the driver was going at a slow speed. Before we summarize the main point, let's graph one more scenario to see if we can observe the same insights, or even more insights. Let's graph my student's haircut business that we talked about earlier. The horizontal axis is the number of haircuts n, and the vertical axis is the amount of profit p. The cost was $15 per haircut, and here's our equation for that. Here are the data points that we computed earlier, and here's the corresponding line. Now, what if the cost was $18? I calculated the cost in advance at the top left here, and here's the graph for it. Expectedly, it's steeper than the $15 line. What if the cost was $12? I calculated the data points at the top left again, and after graphing it, it's expectedly shallower than the $15 line. Okay, so we're validating the same trends here that we saw with the miles per hour example. However, there are some things that we have not seen yet. Let's try some more unconventional costs. If we give haircuts for free, meaning each customer pays $0 for each haircut, the data points are as follows. It's literally all zero, regardless of how many haircuts we do. Consequently, the line of this equation is completely flat, along where p equals 0 on the vertical axis. We can even try a negative cost, where we pay our customers to let us cut their hair. Let's try negative $20, where we're paying each customer $20 for us to cut their hair. Here are the data points, and here's the graph. If you look at the vertical axis, you'll notice that we extend the axis down into the negative numbers to account for having negative values of p, and in pink is our line. Now, here's something neat. If you're observant, you will notice that this line is slanted in the opposite direction than all of the lines with positive cost. All the lines with positive cost are going up as we increase n, but the line with negative cost is going down as we decrease n. So far, we've made a lot of observations of the graphs of specific linear equations. Let's now see if we can make things more interesting by talking about linear equations in general, not constrained to any particular scenarios. Recall that we use x to represent any independent variable, and y to represent any dependent variable. Considering all of the linear equations we've seen so far, we can capture their general structure with this equation. Y is equal to some rate of change times x. The rate of change, also known as slope, is how much y changes when x increases by 1. Okay, that may sound a little hard to visualize, so here's an analogy. When we were driving 40 miles per hour, our rate of change, or slope, was 40. So d increased by 40 when t increased by 1. Now, let me clarify something about our definition of slope here. You probably did not learn about slope in this form in your classes. You perhaps learned it as rise over run, or y2 minus y1 divided by x2 minus x1. I promise we'll get to these notions later. For now, we'll just use our definition with slope as basically just the rate of change. And just some more housekeeping stuff before we're moving on. Let's assign a variable to represent this rate of change. And to match what you learned in school, let's use none other than m. Here's a table summarizing all of the trends that we noticed when we worked with m in the previous driving and haircut examples. Feel free to pause and take a look, and there's also an image of this in the description as well. We're headed towards the end of this first episode, so let's summarize all of the main points we learned, as there were quite a few. Firstly, we learned how to construct equations to represent real-life linear relationships. If you want to think about it in terms of school, we essentially did word problem practice. Secondly, we created visual representations, graphs, of linear relationships. Thirdly, we defined x to represent an independent variable and y to represent a dependent variable. And since these were kind of abstract ideas, we used real life scenarios like haircuts and driving to make sense of these. And lastly, we observed a slope in a variety of ways, as a measure of steepness and an indicator of either increasing trends or decreasing trends. And all of the specifics that we learned about slope, like we showed in the table in the previous slide, will be in the description. This was my first attempt at making an extended math exposition video, so please like and subscribe if you enjoyed it or learned something new from this video. Thank you so much for watching.